Hide the photo meeting controls in business. All right, great. Hi, everybody. We'll get started. We are mic-less for the moment, so I am staying behind the podium, which I normally do not like doing, but just to make sure people on Zoom can still hear me around once we have a mic. So one thing, make sure you fill out the pre-semester survey at some point soon. This is make sure we can assign you properly to a discussion section. So you can either scan that QR and start it now, or you can do it later. There was also an ed post about it. There's a reason we keep reminding you about it. It's critical. It's critical. Okay. All right. Let's do next slide here. So to go to next slide, you got to make sure you're on the clicker too. Okay, so we are recording. Let me just double check that we are recording. We are. So let's dive right in. Another reminder for the pre-semester survey. So just to make sure that our system for getting all your responses in is working, this is how we're going to be checking attendance for the semester. You can either come attend in person or you can attend on Zoom. But we're going to use something called Slido. So if you don't mind, give that a scan and go ahead and enter the emoji that best describes your mood today, just to make sure it's working. If anyone's having issues, let me know, because then we can debug on Slido. Once we do this once, it's usually fine for the whole semester.
Did we mute them?
Okay, no biggie. Yeah. All right, let's see if we've got some responses. So it looks like we don't have any responses. Are people running into issues trying to go into Slido, or are people able to enter answers? Good, entering answers, fine. Let's see. Wasn't letting you enter.
I logged in, but it's in Q&A polls and other polls.
So it's not under, okay, one of the questions. Okay, are Sarah or Ella, you want to check on Slido? Let's just make sure it's open. Okay, it wasn't open for voting, so it should be open for voting now. Let's see, try entering one more time, and if not, we'll have Slido either for the next Slido today or tomorrow. Any luck? Still not able to vote? Okay, Ella, maybe debug this. We'll come back to this in a little bit. Yeah, go ahead.
Is it in the enter your question?
It should be as soon as you scan this, it should come up with this question, so it's not showing up. Okay, that's fine. We'll debug this, come back to it. We have another Slido in a little bit, but Ella, why don't you try figuring that one out? Okay, all right. So anyway, you're typically going to use the QR code at the top of any slide to post questions to Slido. So we'll always have a TA in the room actively answering your questions on Slido. You can also raise your hand. We can also call on you that way. But sometimes we don't have time always to pause for every single question. So you can ask questions right on Slido. They'll get answered. We have a new system actually implemented this summer that's going to allow us to answer questions even better and faster on the back end. You don't have to worry about any of that. But please be generous with your questions. Ask as many as you'd like. All of those questions will also be posted to the website after each lecture, so you can see what other students asked. Okay, so for the attendance policy, rather than bore you with this today, read the syllabus. Syllabus is long. There's a lot of information there. Make sure you go through it in full. The expectation is after the first week of the class, you have fully read through that syllabus. Okay, and then we're also gonna have snacks starting with the next lecture. So while you're not required to come to lecture, there's our sort of benefits to coming to lecture, including just learning how to learn in person. Most of life happens in person. It's a good idea to come to lecture in person, but I'll also bring candy and snacks, and I'll provide Michael with some to bring too. So we want to try to get you coming in. All right. So let's do some quick intros, and then we'll dive into a case study. So I'll start with me. I'm Josh Grossman. I've been an assistant teaching professor at Berkeley for about a year now. This is my first summer session. I did my undergrad degree in neurobiology, which I always like to tell students because you don't have to get things right the first time. I know it can feel when you're, 18, 19, 20, 21, 22, like you have to get things right now or your life is ruined. It's not the case. Things have worked out okay doing an undergrad degree that is completely unrelated to what I do now. I did my PhD about a year ago in computational social science, taking the tools of computation in statistics and applying them to questions in social science. My research during my PhD and a little bit now is broadly at the intersection of data science and public policy. Did a lot of work with racial discrimination in education settings, college admission settings, and also in the criminal justice system. Feel free to check out my website for more info. Courses. This past spring, I taught Data 100. This summer, I taught Data 100. In the fall, I'll be teaching Data 100. And I just learned right before this lecture that I'm probably going to be teaching it in the spring as well. So lots of Data 100. I also teach a smaller class called Stat 131A, kind of like Data 100 Lite for data science minors, also in R, maybe a little bit more of a statistics influence. Between college and grad school, I didn't jump right into grad school. I worked at a company called IXL Learning. Did anyone use IXL Learning when they were in high school? Yeah, about half the country uses it. It's an awesome product, not a great place to work, but I worked there for 2 years as a product manager, got a lot of great skills. I'm a big advocate for taking time off, and you can feel free to talk to me about that, either just casually or also, and people can see the bottom of the slides okay, even though, okay, it's not too obscure, it's a little obscure for us. So you can sign up for a 15-minute chat on my website. The link is also on the slide here. So I like to leave myself open to students. I have 15-minute coffee chats most mornings. If you ever want to schedule, those tend to fill up pretty quickly, and they've been pretty successful this past year, so I'm going to do them again this summer. We often go longer than 15 minutes. So, they're just slotted for 15 minutes. And you can come talk about career, life. Typically, this isn't related useful for sort of course concerns, sort of reserve that for office hours. But if you just want to talk about, where things are headed for you, feel free to schedule a chat. But with that, I'll hand it over to Michael to introduce himself.
Hello, I'm Michael Shao. I am a lecturer here at Berkeley Data Science. I'm more of a Berkeley native. I did my undergrad and my master's here at Berkeley. I did my undergrad and master's in statistics, and also have an undergrad in environmental science. I'm basically like 5 years behind Josh. I'm starting my PhD in the fall in data science at U Chicago. So this is my kind of last endeavor at Berkeley. So I do my research in interpretability and uncertainty quantification. So if you ever learn about confidence intervals, uncertainty sets, that's kind of where I work at. But not only that, I have also worked on a number of data projects throughout my research career. Some fun ones. I've studied marijuana legalization, studied California wildfires, as well as more kind of industry focused Airbnb and other pricing models. This is my first time teaching Data 100. I usually teach the kind of the other class, the other big class in data science, Data 140. I've been a TA and recently an instructor for that class. I've taught Stat 134, which is another probability class, last summer, and then some other classes in statistical inference. So more of a theoretical person. This is kind of my first more applied class to teach. So if I ever bore you with a theory, let me know. You can, that's not really what we'll try to focus on here. So yeah, I'll hand it back to Josh for what do we have next? Logistics and
All kinds of
other stuff. Yeah.
So Michael might be 5 years behind me in PhD, but he's 5 years ahead of me in probability knowledge. So if you ask a really hard statistics question, I will probably send you to Michael. So a couple tips just about us. First of all, you can call us Michael and Josh. If you feel more comfortable calling us Professor whatever, that's totally fine, but we're on a first name basis. So please call us Michael and Josh. And also feel free to say hi in public. It's okay if we don't know you yet. We'll know that you're from our class and saying hello. Unless you have a private question for us, typically don't use our personal emails to get in touch with us. Send an email to Data 100 instructors. This is all in the syllabus. It's all on the course website. I just want to remind folks, avoid our personal emails unless you have a private concern that only one of us should see. Okay? We're always going to have office hours after lecture around the corner in Hearst Field Annex B1. So we're in A1. It is in B1. I've never been to B1. I don't know if it's around the corner, but I think around the corner. Like, two corners away. Okay. Always after lecture. And so if I'm lecturing, all of office hours, Michael's lecturing, he'll have office hours today. It's both of us. And no prep is required for office hours. We want to talk to you. Really, I want you, invite you all, please come to office hours. There is nothing you have to do ahead of time before office hours. You don't even have to come with a question. People who take classes with me and Michael will often say that one of the best parts of the class is coming to office hours. And we'll also often hear that people figure this out too late in the class. 3/4 of the way, they decide to come, and they always tell us, I wish I started coming sooner. So please, please come by. We want you there. We always talk about lots of great things. We usually do it sort of as a group setting. It's not like one person at a time. And then also just keep in mind, cool opportunities, contacts, letters of rec often originate through interactions and office hours. So not only do I suggest that you come to our office hours, but also office hours of other instructors that you might have. All right, so we'll go ahead and start with a case study here. So what is data science? So I could give you a bunch of slides, and I just want to make sure everybody on Zoom can hear too. Yeah, looks like we have some folks on Zoom. If there are issues on Zoom, feel free to post to Ed, just for folks on Zoom. Okay, normally I walk around a lot when I teach too, so you can see I'm moving my arms all over the place because I can't move my feet. So starting with the next lecture, let's hope the microphone is working and I'll be able to run around here. But for now, I'm going to stand right here. So what is data science? What is data science? Again, so I could give you like a long list of like definitions here for data science, but I've always found it's not the most useful thing, especially when you're learning what data science is. So instead, I'm going to give you a case study. So this is a very, very recent case study. This is in the past 2 years, this research started being publicized. And it's one great example of data science being used to drive positive change in the world without a lot of fancy modeling. Now, of course, in the actual research, you can go look, they do sort of things beyond the 10 slides I'm going to show you right now. But fundamentally, their core result is just a matter of doing really good exploratory data analysis and really good visualization. One note too, this case study I'm going to show you by, it's a little bit obscured here. I want to turn off this annotate. Can I turn this off? How do I turn this off? Is that just going to stay there? Maybe it'll just stay there. By Elzane et al. It was just published a couple months ago officially. But keep in mind, this study is about racial bias. Difficult topic, but I think really important to discuss in the context of statistics and data science, because we can see what data science can answer about racial bias and what it can't answer. And understanding some of these concerns is really, really useful for making us more informed and impactful data scientists. So just keep that in mind. Please engage to the extent that you're comfortable. So about 2 years ago, there was a very, very troubling headline in the New York Times. A very, very troubling headline in the New York Times. Black Americans are much more likely to face tax audits than non-Black folks in the United States. Okay, systemic discrimination and how the IRS audits taxpayers. This was 2 years ago. So a couple things to define here. First thing, the IRS. This is the Internal Revenue Service. This is the federal agency that takes your federal taxes out of your paycheck if you've had a job before at the federal level. A tax audit, this is when the IRS suspects your taxes are incorrect for some reason. Keep in mind, tax audits are burdensome to the IRS. They have to go track you down, and they can also be very burdensome to taxpayers. If you actually avoided paying your taxes, then maybe that's a good burden. But if you got one of these tax audits by mistake, it can be kind of scary to get a letter in the mail saying you have to start organizing all of your financial information, and it can take a lot of time. And if you don't have a lot of time, that can be very stressful because you don't want the government coming after you. Now, discrimination is a pretty difficult term to define. There are forms of discrimination that when I say discrimination, you probably think about. But for now, let's think about discrimination as an unjustified difference. That word's pretty loaded. What is an unjustified difference? In both decisions, so the decision-making stage, and also the outcome stage across what are called protected characteristics, things like race, gender, and age. Here's the big mystery for you. Race is never provided to the IRS. When you fill out your tax return, the IRS never sees your race or ethnicity. So then how can they discriminate? How can this be going on? Okay, that's the big mystery we're going to try to solve here, and we're going to see what kind of things with data science we can use to try to come to these conclusions and see these outcomes. Okay, I want to turn off this annotate thing. All right, so as sort of an initial step, we want to calculate these two statistics, X and Y here. We want to know what percentage of Black taxpayers were audited and what percentage of non-Black taxpayers were audited. This was a decision by the researchers to use black and non-black as the comparisons here. They could have chosen another one. Historically, this is a pretty important comparison to look at. And so that's why we're comparing these two groups. So a couple things here. So throughout the course, we're going to try to point out human contexts. Okay, we don't want to just think about data as data in a computer. We want to realize that it's sort of situated in the world somehow. Why does this comparison matter? And you might think to yourself, like, why, what's sort of implied by X and Y being different? Is that necessarily bad? Are there reasons that could happen that don't necessarily imply discrimination? Okay, so keep that in mind. And then the second thing is, even though this looks pretty simple to us now, a huge part of data science, I'm talking about like almost most of the time you're going to spend doing exploratory data analysis, is spent computing statistics across groups. And in this case, we're just comparing two statistics. Okay, but ultimately, this is a huge part of what you're going to be doing in this class. Okay, because we can already see we're starting to elucidate lots of interesting information once we start breaking out statistics by groups. In this case, our groups are black and non-black taxpayers. So here's what the IRS does have access to. On the left, we have a tax return, at least the top of a tax return, a 1040. So the IRS has all the information in the tax return. Remember, it does not have race. It does not have race in the tax return. And then the IRS also has information about whether or not the taxpayer was audited. Okay, so we have outcomes, whether or not the taxpayer was audited, and we also have the tax returns. So we know this from data from the IRS, but we don't just call up the IRS and say like, hey, can we have some audit data? Okay, this is a years-long partnership. Often the hardest part of data science is actually getting the data. Okay, doing the actual analysis can sometimes be very quick. Your basic analysis that you want to run might be a couple lines of code. In this class, we're going to be handing you a lot of the data, but keep in mind, data does not just sort of spring forth. This is a very, very hard part of data science. It's often really messy too, right? Personal connections are really helpful here. Being able to socialize, understanding personalities. This is a huge part of data science, okay? Now keep in mind, race isn't anywhere in this tax return. So already there's no way for us to absolutely determine for sure the race of each taxpayer. Already we're making assumptions in order to run this analysis, but we want to be explicit about those assumptions. And that's something you're going to do a lot as a data scientist. Now the question I have is, can we make an informed prediction of race and then somehow use that prediction in an analysis? So is there any way to use the information in the tax return to actually get a sense of what the race of this taxpayer could be? Okay, so let me give you a little bit of intuition to think about this problem. So for lots of different reasons, cultural reasons, historical contexts, discrimination, the prevalence of hometowns where people live, okay, first names and last names differs quite a bit across race and ethnicity. And again, human context here. Think about, why do these differences exist? Are they all necessarily bad? On the left side, we can see census data from the 2020 census conducted during COVID in Berkeley. There are about 125,000 people recorded in Berkeley, and we can see there isn't an even number of people from each race and ethnicity. So we can see in Berkeley, there's a difference in this race distribution, this race and ethnicity distribution. On the right, this is a very specific set of statistics here, or rather a very specific summary. This is from 2013 in New York City. We can see the most popular baby name across 4 racial and ethnic groups. We can see that the most popular baby name is different. And if you look at the list of all the most popular names across these groups, there are quite a lot of differences. There's overlap, but there are differences. Okay, so there are differences in first names, last names, and hometowns between racial and ethnic groups. And so maybe we can take that information, which we get from a tax return, hometowns, first names, and last names, and try to say something about race or ethnicity. So let me give you a little bit of intuition here. New York City skyline on the left. In 2020, about 16% of New York City was Asian identifying. Right side San Francisco skyline, about double, twice that, 34% were Asian identifying. So if I handed you 2 tax returns, and the only thing I told you about those tax returns was one is from New York City and one is from San Francisco, you would probably say there is a higher probability that the San Francisco tax return is from someone who's Asian identifying. You used information about the distribution of Asian residents across those 2 cities to tell you something about that tax return. Okay? We're using probability here. It's inescapable in data science. We're going to be talking about probability. We have a couple lectures on probability in Data 100, and there's more probability courses that I encourage you to take in the future. And so using that intuition and sort of scaling up this intuition to first names in very specific areas called census block groups, okay? Scaling up this intuition with first names, last names, and census block groups, we end up with data that looks like this. Robert Johnson from some particular neighborhood in New York City has some probability as identifying as Black. Tanisha Tompkins from neighborhood B in San Francisco, same idea, and so on. And so we've used this model, and it's a relatively simple model based on sort of standard probability principles. No super fancy machine learning going on here, okay? We now have predictions for race and ethnicity for all of these taxpayers. And these were validated against real data, and these predictions are pretty darn good, okay? So now, and need some links to the algorithms if you're interested. I'm happy to talk more about those offline. Notice we brought in some external data sets to run this analysis. We needed to go find the distribution of first names, the distribution of last names, the distributions of hometowns. So we're going to be learning about this in this class. How do you bring in external data sets to make your analysis a little bit more punchy? So let's visualize this data. X-axis, we have the estimated probability of identifying as Black. Okay, we saw before from that prediction, we're going to get a 0 to 100% probability that a particular taxpayer identifies as Black. The y-axis here is the probability that that taxpayer gets audited. Here's the plot. Each one of those points is an equally sized group of taxpayers. So you can see there's more density on the left because a minority of people in the United States identify as Black. And so we can see that more folks are sort of clustered on the left side here. We can see a pretty clear pattern. As the estimated probability of identifying as Black goes up, the audit rate goes up. And not just by a little. We're talking 3 to 5 times higher. Okay, so what could be driving this, right? We have to sort of like question our analysis here. What could be driving this? Is this necessarily discrimination? Remember, the IRS never sees race. So how could this be happening? Well, you might ask, okay, well, what's probably the most important number in a tax return? What's the most important number in a tax return, arguably, that somebody might enter in their tax return? Income, right? Income. So let's say this. Well, maybe this is a story about income, and it's not a story about race. And so let's adjust for it. We're going to learn about linear regression and logistic regression for adjusting for things like income using a model, but we can adjust visually. We can adjust visually here. So on the x-axis, we have reported income. The y-axis, we have that same audit rate as before, and we're going to plot now what is the audit rate for Black and non-Black taxpayers based on income. And when we do this, we get another interesting pattern here. So rather than try to describe what this pattern is, right off the bat here, what do you think could be responsible for the patterns in this plot? So let's try Slido one more time. Should work. Okay, let's see. What's that? Before it was asynchronous. Oh, okay. Let's see. Yeah, once people start entering numbers, the number in the top right should start increasing. Let's hope it works. What do you think could be driving some of the patterns in this plot? And there's not just one pattern here. What do you think? And if for whatever reason you're not able to enter it now, you can enter it asynchronously because it looks like the number isn't going up. We got to debug Slido and see what's going on. Oh, good. We're working. Okay, I'll give you a little bit of time. If folks have questions, feel free to raise your hand. I can come around and clarify. This is a complicated story. So I'll let you keep writing in here. But let's see what the word cloud is starting to look like. Keep in mind, all of these lecture participations are graded just based on participation. You can literally enter whatever you want. But we sort of are intentionally choosing questions to help prepare you for exams and also to get you sort of thinking about sort of bigger questions. Okay, so we're seeing some answers here about income. There's something with low income. Okay, other things, socioeconomic factors related to incomes, gentrification, okay, something having to do with neighborhood. And so everybody seems to be saying here that there might be another factor that's responsible for this, right? We don't necessarily just need to adjust for income. There might be something else that's explaining this pattern. Because I know I keep reminding you, but remember, the IRS never sees race. So this cannot be an explicit decision made by human auditors. Okay, so let's see. So as it turns out, the IRS uses an algorithm to help them flag which tax returns should be audited. And this isn't necessarily bad, okay? This isn't necessarily a bad thing. This algorithm might do a good job of picking the tax returns that a human auditor would have picked, okay? But we have to scrutinize any algorithm that's doing this, right? To make sure that it's working correctly. But ultimately, if this algorithm can save auditors a ton of time, then those auditors can spend their time on more complex cases that might result in recovering a lot more money. So algorithms aren't necessarily bad. I don't want you to be afraid of algorithms, okay? But we have to scrutinize them to make sure they're working correctly. And so as it turns out, what was going on with this algorithm was that it was prioritizing errors in claimed tax credits. So a tax credit typically used a lot by lower income tax filers. If you have a certain number of children or you have a certain income, you can check a box and your tax burden is automatically reduced. It's essentially like the government is giving you money because you don't have to pay some amount of taxes. And what was going on was that this algorithm was prioritizing catching people who made errors on their tax credits. And keep in mind, it's not a simple process. These aren't necessarily malicious errors. Somebody without a lot of time, without a lot of income, it might be hard to read through all those tax forms to get things correct, right? We all might struggle with it. The algorithm was prioritizing these tax credit errors over income underreporting errors. And so, for example, a tax credit error that would have recovered the government $500 if fixed might have been deprioritized relative to an income underreporting of $5,000. Okay? And so somebody who made this algorithm, it's very reasonable to say, well, let's try to make sure that people who are making errors on their tax returns are caught. And everyone's like, yeah, let's make sure errors are caught. But not just the fact that whether an error occurred is important, but maybe we should be thinking about how much money each error could recover, right? If we recover 100 errors that all recover just a little bit of money each, we'd much rather get this big fish, right, who screwed up their tax returns in some way. Okay? And so this was what was going on under the hood. Really important to think about, what is your metric for success? And that wasn't just the end of it. They didn't just report this and everyone was like, oh, wow, interesting. The IRS said they were going to change things. Okay, and this was about 2 years ago. I haven't followed up to see how things have actually changed internally within the IRS. We know there are a lot of changes with administration changes at the IRS. But keep in mind, like this example, and notice, again, no fancy modeling here, just good exploratory data analysis really led to very big change. Okay, all right. I like to say this because you can improve the world with tools from Data 100. This isn't just sort of like a blanket statement. These really are the tools that can change things going on in society. Okay, why don't I pause just for questions about the case study, if anybody has any. Yeah, right in front.
I'm not a public policy person,
Sure.
so I don't know. Please correct me if I'm wrong or someone else correct me. But I feel like something that could be contributing to this is like I read that, and I don't know if this would have been worked into the algorithm or what, but that there was a priority placed on success of like pursuing the case, and that some of those big fishes had higher rates of fighting the IRS on it, and either leading to a failure in pursuing it, or just like a huge waste of time trying to fight them on it. And so that it came down to like, well, we end up recovering more money with small fishers because they can't find us.
Interesting.
Which would then also contribute to discrimination because those are people who are already tired and work more hours, et cetera.
Great. So one of the questions I was just asked, to repeat it for folks on Zoom, was that another factor that could be taken into consideration here is the IRS's decision to pursue either more complex tax returns or less complex tax returns. Less complex tax returns are more easy to audit relative to more complex tax returns that typically are associated with higher incomes, large companies, these sorts of things. And maybe the IRS has only so much budget in what they can actually act on that they end up prioritizing those less complex tax returns. Absolutely part of the story. Okay. Other questions? Other questions? Yes.
Are being audited more, how would you go about it from the start? What would you do differently than what was done to actually get this data?
It's an excellent question. Unfortunately, in the 5 seconds I have to think about it, I don't know if I'll be able to give a great answer. Why don't you come to office hours after and we can sort of think through it, because it's an excellent question. You know, this is a nice thing in data science when you're trying to solve a problem at the beginning is to think about, if you had infinite time and if you had infinite money, how would you do it? And then try to work your way backwards and see how close can we get there. Okay, it's a really nice way of thinking about the problem, because conducting an experiment like this would be very complicated, right, to get right. It might not even be ethical to do it in the right way. So anyway, come to office hours, we can talk about it. It's an excellent question. And just to repeat the question was, how would you do this if you could go back and run an experiment to actually go try to figure this out definitively? Is there sort of a better way to do this with infinite time and infinite money? Other questions before we keep going here? Let's take a third one, and then we'll get into course logistics. Okay. Anything from Slido worth mentioning? No? Okay. All right. Why don't we keep going? So this class is all about data science, right? So we just talked about what data science is. This is an old diagram that's still pretty relevant about where data science sort of fits in the world. Some combination of hacking skills, being able to code, math and statistics knowledge, and also substantive expertise. So how does all of this sort of come into play? Somebody need to actually go get that IRS data into a usable format. Someone need to actually go write the code, generate all those visualizations. This is where the CS side of things come into play. Math and stats knowledge. Someone had to go design a model for inferring race and ethnicity. That's a sort of difficult question to think about to make sure you're getting sort of your answers correct. Estimating the influence of different variables on audit rates. We didn't talk about this, but how much does income contribute to those differences in audit rates? And then also quantifying uncertainty, something we're going to be talking about in this class. How sure are you of your results? How much precision can you give to your results? We said Black Americans were 3 to 5 times more likely to be audited. How confident are you in 3 to 5 times more likely based on the data? And now really this bottom circle should be the largest here by far, because this is really what allows you to run a lot of analyses. Someone actually needs to go figure out, how does the IRS actually audit? They need to go find their contacts at the IRS and work their way through this whole system to figure out what's going on under the hood. Someone needs to go build relationships there and then actually convince the public, right? They could have included a lot more information in the plots I showed you, but maybe the public wouldn't have been as sort of interested or understanding of the results than they were with the plots they were given. So just keep in mind, data science is a combination of these three. The bottom circle is sort of the most neglected part of this circle. Domain expertise is huge when it comes to data science. Now, another nice plot from about 10 years ago. I recommend taking a look at this offline, especially if it's difficult to read. But if you look at the bottom left here, basic exploratory data analysis, 70% of data scientists said that a major part of their job was basic exploratory data analysis, which is a huge part of Data 100. This is sort of the bread and butter of data science. Okay, I've heard before that the most powerful data scientist is someone who's really good at SQL and really good at PowerPoint. Okay, it's a really nice quote to remember, because at the end of the day, really fancy modeling is useful, but for answering a lot of big questions, at least initially, all you need is that basic exploratory data analysis. But you might come back when I say that and say, well, can an LLM just do all this? Can a large language model like ChatGPT or Gemini go do a basic exploratory data analysis? You all may have actually thrown a data set into ChatGPT before and asked it to do things with that data set, and everything that it outputted looked pretty valid. And so my question to you is like, what is sort of the future of, let's see, what's going on here? We've got a different Slido. Hold on. This is the wrong Slido. We're going to iron out all these bugs for lecture 2. Let's see. Great. Okay, well, we were supposed to have a Slido asking you to think about the role of Gemini and ChatGPT and other large language models in the future of data science. We won't worry about this today. But a lot of people might be worried. I get this question from students a lot. Like, is my job going to be replaced? Should I be in this data science class right now? How useful are these skills going to be in 10, 20, 30 years? Am I wasting my time? Natural question to ask. So nobody has the answer to this question, right? Ultimately, boy, hold on one second, everybody. Whew. Ultimately, nobody knows for sure. Okay, but Michael and I have hope. Opinions expressed on this slide are me and Michael. I hope, Michael, let me know if you disagree with anything on the slide here. But let me give you sort of a rundown of a basic analysis pipeline. So when you're running an analysis, what do? Step 1, you got to gather context. You got to ask good questions. You got to talk to a lot of folks. Step 2, you actually have to go plan the analyses that are going to address those questions. And step 3 is you have to run the analysis. You can break this down in lots of different ways. Everything on this slide is grossly oversimplified, like the text at the bottom says here. But where do large language models fit into each of these pieces? So I'm going to start with step 3, running your actual analysis. And we can think of this as like writing the code to actually do the analysis you've planned. And LLMs are actually quite good at this. With proper context and instructions, LLMs are quite good at running your analysis. You have to be able to verify the outputs of that analysis, but I think LLMs are sort of the most helpful by far at step 3. Okay, they're very helpful at step 3. Now, step 2, LLMs can sort of provide advice as you think about what the best analysis can be. And talking with an LLM can be quite useful, but ultimately this choice of best analysis is often quite subjective. You really need experience, and not experience in the way that LLMs have experience, to be able to answer step 2 well. So I like to think LLMs are kind of useful in step 2, but ultimately that's something you need to be able to answer with your own data science experience. In step 1, LLMs, at least right now, can't go to a company and go talk to different people and figure out different personalities, different abilities, all their desires, what do they actually want based on how they're talking. This is something you have to go figure out as a data scientist. In this analysis pipeline in Data 100, you don't have to go through this whole pipeline for a lot of this class. We give you a problem set with questions to answer. When you're a data scientist on the job, there's no problem set, right? Like you kind of create your own sort of problem set. And so you don't spend any time thinking about steps 1 and 2 and have an LLM run everything in step 3, it's going to lead to issues. It's going to lead to issues. And so the secret is out. Most Data 100 homework problems can be fully solved by LLMs, like other classes. This is sort of like the new frontier of education. Solutions are no longer a thing, no longer something we can really hide. When you have taken an exam, sure, right? When you don't have an LLM in front of you, but if you have a computer in front of you, solutions are no longer something that can really be hidden. If you have LLMs fully write your answers, I'm saying fully. I'm about to say LLMs are useful for some things. But if you have LLMs fully write your answers, you are outsourcing steps 1 and 2, and you never learn to verify the outputs of step 3. In this class, that can get you full credit on homework. Okay, we try to detect AI as well as we can, but we all know nobody's great at this. Okay, so just keep this in mind. You can do it, but you're setting yourself up for replacement by LLMs. And employers know this. No matter what your degree says, no matter what your honors are, your grades, they're going to go check to make sure you actually know what you're talking about. And those nice stamps on your degree aren't going to do you very well if you don't actually know how to do the actual data science. So just keep this in mind. You have to self-police a little bit here, and we're going to help you self-police a little bit here. So we encourage you to use large language models appropriately in Data 100. I think you're doing yourself a disservice if you completely ignore LLMs. Okay, it's kind of where things are moving in the future. I think you should use them to help you. You want to use them productively. And there's a whole section of the syllabus explaining ways to use large language models appropriately. One way. What does this error message mean? That's fine. That's a great thing to ask an LLM. Inappropriate. That's essentially just copying the homework question into ChatGPT or really closely paraphrasing it. That wouldn't be appropriate. And frankly, we might catch you for academic dishonesty if you're doing that. Okay, in the first discussion, we're going to show you how to install a custom LLM. The instructions are also linked right in that second bullet. Okay, to install a custom LLM in Gemini, Gemini is quite good at data science questions. Some people say it's a little bit better with sort of probability and math than ChatGPT. But we have a custom LLM you can install. It's just a nice prompt that's going to help you use an LLM effectively. It's going to help sort of guide your behavior. Because what we've seen with students is that people tend to want guardrails. There's a large number of students who want guardrails. They don't want the LLM feeding them answers. And this is sort of our attempt this summer to help you out on that front. Feel free to edit the prompt or edit that bot how you see fit. And also, if you come up with edits that improve the bot's behavior, let us know and we can incorporate them. Now, Google is nice enough to give Gemini Pro for free to all students for the next year, and Berkeley will probably give it to you free within the next year. But you have to do it before June 30th. At least that's what Google says. I don't know if they're going to extend it. So please make sure to sign up for free Gemini Pro. It's a little bit confusing because you have to use a personal email to sign up for it, but you have to use your Berkeley email to verify that you're a student. So you're not going to have this through your Berkeley email. You're going to have it through your personal email, but you're just verifying it by providing a Berkeley email. So please, if you haven't been listening this whole lecture and don't plan to listen to the rest, that's fine. Just make sure to do this. Just make sure to install Gemini Pro, and then we'll talk about the installation for the custom LLM in a bit. Okay. What are you going to learn in this class? We have a long list of topics we're going to go through in this course, and we're going to cover them very, very quickly. Big theme for the summer is that Data 100 is fast. I have a slide about that in a bit. But what are some of the principles and techniques we're actually going to cover in this class? Lots of great things. Pandas and NumPy. How do you deal with tabular data? How do you deal with really big tabular data with SQL? How do you do exploratory data analysis or EDA? Regular expressions, often hated by students. I love regular expressions. I think they're awesome. We're going to learn about them next week. How do you manipulate text? Visualization, 3 different packages. Plotly's for interactive visualizations. We're going to be using that a lot. Michael's going to be handling a lot of the statistics here, sampling, probability and random variables. We're going to be talking about how you actually build a model and teach a model to optimize for some loss function. Linear regression, hugely important in the world, hugely important. Really deeply understanding linear and logistic regression will serve you so well going into the future. Feature engineering, other ML topics like gradient descent, logistic regression. Towards the very end, we're going to be doing something called clustering. How do you group similar observations together? And then finally, the sort of capstone principal component analysis, what's called an unsupervised learning technique. But keep in mind, these are all just tools, right? A lot of people think data science at Berkeley is like, this big bucket. You got to make sure it's really filled with all these methods. And if you don't have enough methods in there, you're not going to be a good data scientist. That is the wrong approach to take. You want to really deeply understand the fundamentals, a lot of the things on this slide. And then again, just keep in mind, these are all just tools. On the job, you might be using a different tool. There might be a different tool that's introduced in 3 years. You might be using R. I mostly use R. I don't really use a lot of Python in my analyses. Classes in Python. But just keep in mind, more importantly in this class, you're going to learn how to reason with data. You're going to learn how to take the skills that were in this class and apply them elsewhere. Okay, everything is very applicable elsewhere. You don't have to take another data science class to learn everything in this class in another language. Okay, course overview, the fun stuff. Let's talk a little bit about what we're going to be doing in this class. Prerequisites. All of this is in the syllabus. You probably weren't able to enroll without these prerequisites. Got to make sure you finish Data 8. We're assuming knowledge of Data 8, assuming knowledge of 61A or 88C, and then either you've completed a linear algebra class or you are enrolled in one right now. Okay, that's going to be an assumption. We know that people are enrolled in linear algebra right now, and so when we get to heavier duty linear algebra topics, we will provide additional support. Okay, we're not assuming you've already finished an entire linear algebra class. We're not going to teach how to use Python, even though you're going to be using Python in some way, sort of the basic implementation of Python, or how to use Jupyter Notebooks. That's going to be our computing environment for the class. All of the inference from Data 8, we're going to review to some extent, but make sure to take a look at the inference from Data 8 because we'll draw on it heavily. And then I already mentioned linear algebra. Homework 1 and Lab 1 will help you see how much linear algebra and coding you need for the course. Okay, and if you're feeling unsure, get in touch with us. We want you to succeed in this class. We have a ton of support in this class. this summer. Okay, we have a ton of support. So we want you to succeed in this class. Staff. So speaking of support, we really have a rock star staff this summer. And I know professors will often say that before every class, but we really have an incredible staff this summer. These are some of the best of the best. Okay, head TA, we have Jake, Shaoray, Sammy, Milena, and Wesley are our TAs. These are the folks who are going to be leading discussion sections. Okay, lots of them have, all of them have course staff experience either in Data 100 or in another course. So do all of our UCS1s, our tutors, Ben, Christina, Ella, Justin, Rohan, Hannah, and Sarah, some of whom are here. I think Rohan is right here. Ella's right here. Sammy's right here. Sarah's right there. Anybody else I'm missing? I don't think so. Okay, UCS1s are also fantastic. Many of them have been UCS1s quite a while in Data 100 and have tons of experience that they can help you with. Some logistics, content and workflow in this class. So we have the syllabus. The only thing I want to point out in the syllabus, I'm a little hesitant to click on this because there's been some weirdness with Slido. The main thing I want to point out in the syllabus is the exam schedule this summer. Definitely read the syllabus. I'll give you the high level now. This summer, we're going to be trying computerized exams in Data 100, okay, with slightly different versions that, depending on what time you show up to take this exam in our computer-based testing facility, you might see one version or another version. So that's for the midterm. We have computer-based exams. Based on how that midterm goes, okay, our final will either also be computerized. Ideally, going forward, Data 100 is going to have computerized exams going into the future. But if for whatever reason something goes wrong, we will have a written final, a two-part written final during lecture time, last 2 days of class right here. All of that information is in the syllabus. The computerized versions you take in a single sitting on one day. If we have that written final, it'll be over 2 days. Feel free to ask questions about that on Ed. Keep in mind, we are piloting a lot of new things this summer in Data 100. We are going to be flexible. If things go wrong, you will not be the ones punished. Okay, we will self-punish for those things. All right, course websites and platforms. Where is all of your work going to be submitted? Where is all of the information about the course? So course website, that's always where to start. Course website is right there. Okay, all the previous course websites for Data 100 are also available on there. Lectures, assignments, discussions, they're all posted there. We do not use B courses in this class. We do not use B courses. All that B courses is used for is a link to that website. Okay. Data Hub. You probably have seen Data Hub before. This is where all of your assignments are going to be worked on, except for written assignments. Any link to an assignment or to a lab on the website will automatically take you to Data Hub. If you have a Berkeley email, it'll be very easy to get right in, and you're going to get a nice Jupyter Lab interface. Ed is where all the discussion in the class is going to happen. In general, if you have a question, it should be on Ed versus email. It's much easier to track on Ed and follow up, and other people can benefit as well. Lean towards public questions to the extent you can. Let others benefit from the knowledge that you glean from a TA. Rather than benefiting just one person, you can benefit 150 by making your question public. That's also where all of our announcements are going to be. We are not going to give announcements over email. Ed might send an email notification, but make sure Ed notifications for announcements are set so that you can get all of the course communication in this class. Now for grading, we're going to use something very similar to Gradescope called Pensive. You might have seen ads for it around the campus. So Pensive has two products. There's like a tutor. We're not using the tutor. You can use like that Gemini bot we talked about, but we're using Pensive for grading. Okay, the upload will look very similar for all of you. On our end, it's going to speed up grading substantially and give you better comments back. And that isn't just time that we save. That's not the goal. The goal is now we have all this extra TA and tutor time that we can spend office hours on answering Ed questions. It all sort of benefits you without any sort of hit to grading, okay, or grading quality. It's kind of a free lunch for everybody. Okay, but anyway, we're going to be using Pensive for grading, so just keep that in mind. Not Gradescope, but very similar. The lecture notes. I saw a couple people make this mistake last semester. Think of the lecture notes as the unofficial course textbook. There is a textbook for Data 100 that we link, but it is supplemental. There is some overlap with the class, but it's not going to cover some things in enough depth, and it's going to cover a lot of things in a ton of depth. It's an excellent textbook, but if you're going to read in this class, start with the lecture notes, and if you have time, you can check out the textbook. but think of the lecture notes as the unofficial course textbook for Data 100. We'll always have the old lecture notes posted before each lecture. So if you go to the website, all of the lecture notes are from spring 25. And then as we maybe change things in some lectures, the lecture notes will be updated. We have a lot of sort of heavy improvements to lecture notes coming this summer. So you can look forward to that. I think that's the end of all of the websites. This is what the Jupyter Lab interface looks like on Data Hub. I'm just checking the time because there isn't a clock around here. The Jupyter Lab interface, you're going to be very friendly with this over the summer when you're filling out all of your assignments. There's also a quick slide here. I'm not going to go through all of the bullet points here, but lots of good tips and tricks for using Jupyter Lab, lots of little nice keyboard shortcuts that are sometimes worth learning. You can take a look at all of those links sort of offline. Okay, summer will go by fast. This is a already pretty fast course condensed to 8 weeks instead of 15. We are going to be moving at blazing speed this summer. It's almost like a full-time job. The summer edition of Data 100 is fast. Most weeks, 4 90-minute lectures or 80-minute lectures, because we usually start 10 minutes late. 2 discussions if you choose to attend discussion. Take a look at the pre-semester survey to see your choices about attending discussion. I highly recommend going to discussion. We've got some great TAs this summer. 2 homeworks each week, okay? 2 homeworks each week. We're not going to release them 48 hours or 72 hours before the next homework is due. Okay, we're not going to do it that way. We're going to try to release homeworks a lot earlier so you can start working ahead if you want. Okay, but just keep in mind, 2 homeworks are going to be due most weeks. Some weeks have 3 because there's a holiday on the previous week and it gets pushed. Just keep in mind, we are moving quickly. And then 2 labs, which are graded on, essentially graded on completion because the answers are all provided in the walkthrough video. This is nearly a full-time job. This would be difficult for me back when I was in college, but you can do it. And we have a lot of support to get you there. The most important thing is don't go MIA. Don't go missing in action. Don't be silent. If you start falling behind, as soon as this week, get in touch with us. We can help you get back on track. Okay, we have a huge infrastructure set up to help catch you up. To that end, we have 2 optional catch-up sessions each week that will be taught by Sammy right here. These are going to be an excellent way to stay on top of the course material, even if you're not necessarily behind. They're going to help synthesize all of the lecture material for you and prep you for the homework and exams. We'll also have exam review sessions separately, but just keep in mind, those are sort of special for the summer. And then like I keep mentioning, the summer has a couple experimental components, and all of these are intended to make the class a lot better. If anything goes wrong, we will be fair and flexible. Again, the onus is on us to get this right. You will never suffer from these experiments. Okay, the goal is for all of you to benefit a lot. We've really thought through these very, very deeply and chosen some key things we want to try this summer that are a little bit new. Okay, discussion sections and TA and tutor office hours start on Wednesday. So the first discussions are open attendance. You can go to any discussion you want, including the online discussion. Keep in mind the online discussion is reserved for people who are unable to come to campus this summer. If you're all here now, probably not the option for you. On the form, you have to explain why you're not able to come to campus. But Michael and I have office hours starting today, and Ed is open starting today. So again, right after lecture today, right after lecture tomorrow, for the rest of the term, Michael and I will have office hours right after lecture. And again, post to Ed if you have questions before Wednesday that maybe a TA or tutor can answer for you. Yes.
So then you have office hours after each Monday through Thursday lecture?
Every time.
Holy shit,
Right after.
awesome.
Right after. So this way, you know, if you have questions about the course or about the lecture we just had or anything else, and you're already here. Another reason you should come to lecture, because you can just walk with us right over to B1. Yes.
What time is it?
What time is the office hours? Right after lecture. So the other office hours. Yeah. The other office hours are all during the day, spread out, and most of them are held in Warren Hall. Take a look at the syllabus. A lot of this is explained more in detail, and also the calendar for office hours is on there. We also will have online office hours, I think from 6 to 8 most nights of the week. It might be every night of the week, most nights of the week. And then our office hours are right after lecture, 12:30. We can start talking in here and walk over there together. There'll probably be leftover snacks starting tomorrow. No snacks today. Okay. Interlude. Shall we do a 2-minute stretch break? Quick stretch break. We got 20 minutes left. Go ahead. Quick stretch break. Get up. Probably don't have time to go to the bathroom. Hang out. If you have a quick question, raise your hand. I'll come to you. Or one of our TAs will.
I was excited for summer.
Woo. Yeah. Yeah. Super excited.
Sorry, I can't like so boring. Last here over the summer, so fun. Taking classes over the summer, highly underrated. Show up to my discussion on Candy. We're gonna make new friends. We're gonna try hard problems, and you got it. Okay, it's gonna be fun.
What's their best? What's that? It's as opposed to being like this for the mega section, you'll be in a smaller room, just a couple people. Oh. Yeah. Yes.
I mean, I'm definitely gonna go to your office anyway, but, I took all 54 of the language, so I'm not going to students on facility. Okay, I have already looked through these other ones, so. God, yeah, but, you know, on path, whatever. I did check out the source. So that's great. The biggest issue for me is I said all the time.
So it's a lot of things that
linear, when I was doing that here, and I barely passed it like before. So I like wasn't nervous about that. My God. I checked out your website for it. Nice field. Go try to go again. So we'll talk later. We'll talk. Sorry about it.
I wouldn't worry about it.
Okay.
Awesome. Any other personal questions? You can also ask him right after. Yes. Oh. Okay, should we wrap up? Let's wrap up. We got 20 minutes to go. Last semester, I, for whatever reason, always thought class ended at the 20 and would end class early on accident. Everyone would give me confused looks. If I do that this summer, you have to tell me we have 10 more minutes. Okay, quick, some things about the data science lifecycle. I'm just bringing up the data science lifecycle here because it's going to sort of help frame all of the other lectures. I want to give you sort of a framework for thinking about data science. This isn't something you're going to be sort of explicitly tested on, but it's a nice thing to keep in the back of your mind, that data science isn't like a linear path. It's very much like a cycle, okay? So there are lots of things on the internet about a data science lifecycle. They're all kind of saying the same thing under the hood. We have our own, but just keep in mind, they're all pretty much the same. Here's how you're going to think about the data science lifecycle in this class. So this diagram is going to show up before most lectures. We're going to kind of put you somewhere on this diagram. Each lecture kind of falls in this diagram at some place. Okay, it's a high-level way to describe data science. And notice there's two ways to start this, and I think this is easy for people to forget. Because when all of you are doing data science projects, the way you probably think about it is go online, find a public data set, and start in the top right. When research most of the time starts at the top left. You're interested in something. Are college admissions fair? Let's go talk to our contacts in education, see if they have contacts at a college admission service, see if they have data. Okay, most research starts at the top left. But just keep in mind, you might be thinking about things as the top right. Sometimes in research, we end up at the top right. The Stanford Open Policing Project was released one year. Maybe suddenly you have questions about policing and you move from the top right to the top left. But keep in mind, two entry points here, two entry points. How do we ask a question? What are we trying to solve? What are our metrics? We saw this earlier in the IRS example. This is a very human part of data science. LLMs are not great at this step. Okay, they don't have a deep understanding of the world that you have. They don't have the deep personal experiences you have to be able to frame a question. Okay, again, obtaining data. This often takes years of exploration and negotiation to obtain. At a company, you might have data being generated daily, but setting up that pipeline can take quite a while. We're going to hand you the data most of the time in this class, but just remember, there's a lot of work on that back end. There's a lot of work on that back end to get that data put together. Not necessarily by us, right? We might have pulled it from somewhere else. Understanding the data, what kind of biases are in there? Can you actually trust the data? I think this is something that we so often do. We see a bunch of data in a table in Excel and we're like, great data, ground truth. You have to think, can you actually trust this? Is this actually valid data? Understanding the world, taking all of those insights that you've gleaned from data science and actually going out and making predictions. Okay, that's the data science life cycle in a nutshell. We'll be using that throughout the class. Now, we have 14 or so minutes to go, so maybe we actually will start Pandas. The reason I want to start Pandas today and not tomorrow is because there's a lot of material to cover. Again, the summer is fast, and I want to be able to pause and ask questions for folks. So let's go ahead and start Pandas for 15 minutes. Don't worry about pulling out your laptop or anything like that. Just sort of let the information wash over you. We'll start the next lecture either by wrapping up if we don't finish these slides, or with a demo where we'll start actually working with some of the code I'm about to talk about. Okay, so congrats. You've been given a nice box of data. I just moved to a new apartment, so I've seen a lot of the left picture, and I'm kind of ready to be done seeing that picture, but again, we're seeing it today. So congratulations, you've been given a box of data. Okay, how do we deal with it? How do we deal with this file filled with data? How do we actually open it up and start manipulating it? So I want to give you this term, tabular data. What is tabular data? Tabular data is data in a table. This is the bread and butter of data science. There's also non-tabular data, a little bit more complex to deal with, but often in a data science workflow, you're taking non-tabular data and you're trying to massage it into tabular data. Data 100 will mostly work with tabular data, I think almost entirely. The data set we're going to be working with in this Pandas lecture is from all these US presidential elections from 1824 to the present. We updated it last semester for the 2024 election. We can see all of the candidates that ran, even those candidates that didn't get very many votes. Okay. Each row here represents a particular candidate, a particular observation. When we say an observation in this class, we typically mean one row in a data set, one sort of individual, whatever an individual might be. In this case, it's a person, but it might be a company, it might be a school, it might be something else. Columns represent some characteristic about each of those observations, which we often call in this class a feature. In other classes, you might hear other terms like covariate. In my world, we often say covariate. In the machine learning world, my world meaning social science world. In machine learning world, you often say feature. There's going to be a slide later in the class that gives you all of the different ways you can describe these two things, but just keep in mind in data 100, we typically refer to columns as features. In this case, the political party of each person. So in data 8, you used a package called tables. This package was, or table. This package was designed specifically for data 8 to abstract away a lot of the nastiness in Pandas or complications of Pandas for someone who's just learning. But in this class, you are going to learn how to take your knowledge of tables and apply it to this industry standard package called Pandas. Now, why is it called Pandas? The creators may have liked Pandas, but the reason it's called Pandas is because Panda stands for panel data. Panel data, and I'll let you sort of look up what panel data is on your own if you're curious, but the Pandas package is to help you with panel data, which is typically tabular. The Data 100 logo, which you can see here, why is there a panda? Now you know why. Okay, we start off with pandas, we spend a couple lectures on it, and so pandas get an undue influence in the class. At the end of the class, when you finish this class, you can get a nice sticker, just like on my laptop, that has a panda that says Data 100. I don't know if you can see it. No, it's at the very bottom. Sorry, it's obscured. Anyway, finishing the class entitles you to one sticker. Pretty good. And data science skills with the sticker. Pretty good. Okay. What is a data frame? What is a data frame? This is a term that's not just specific to pandas. We also use it in the R world. They also use it in lots of other worlds. But a data frame is how we typically refer to a table of data. A table of data. And that table of data is kind of like a train. I like to think of it like a train, where each train car is a column. More specifically, it's something called a series. It's a data type in pandas, a series. Each column is a series. On the left, we have a data frame that's printed out in pandas. We'll see that in the demo starting with the next lecture tomorrow. But we can see on the right, if we extract that column, something we're going to learn how to do shortly, we get something that's printed out that looks a little bit nastier than the thing on the left, but it's still highly structured. Notice we have indices. We have an index for each element of that series. It looks like we go from 0 to 186. So there are 187 elements in this series. The series has a name. It's called candidate. That's also the name of the column. And then this D type, the data type of this column, is an object. Now, why is it an object? You might say those look like strings to me. The data type object for a series just refers to the fact that the series can store arbitrary Python objects. And in this case, it's storing a string in each element. Okay, to the right side, we have a series. To wrap up today, we're just going to talk about series, and then next time we'll start manipulating data frames. So how do we go play around with these series? So a series, it's a one-dimensional array-like object, very similar to a NumPy array with some additional features. It has a sequence of values, those were the candidates on the previous column, sequence of values, and it also has a sequence of labels that we call indices or an index. Indices is the plural of index. How do we actually go create a series? Well, first of all, we need to import the pandas package, which you'll often see written as import pandas as PD. This way we can refer to the pandas library throughout our code. That's the common sort of abbreviation that's used. And in this case, we're creating a series by passing in a list, a standard Python list with 3 elements. Welcome to data 100, welcome. And we can see it's now been converted into a slightly different object than that list. It's now a series that has a set of values, which we can access by calling s.values. The series is stored in a variable called s. We can access those values by using s.values. And we can access the index if we ever want the index using s.index. The one on the right, you're going to use more than the thing on the left. The range index, you don't have to worry about this too much for data 100. I just want to show you that this is a special pandas object that's hyper optimized because it's always increasing and always increasing by 1. The thing on the right is sort of more useful, being able to access the actual values. Notice we get back an array that looks a lot like a NumPy array filled with strings. Okay, that's the construction of a series. Let's keep going. How can we change the index of a series? How can we change the index of a series? So I can construct a series by passing in a list of values. In this case, my values are numeric. The index can be strings if you want, that's fine. Okay, notice in this case, we don't have 0 through 2 here. We now have A, B, and C as our index. And our numeric values on the right are the values of that series. We can access, again, that index. We saw this on the previous slide. Notice we now have an index of A, B, and C. You might want to index your observations by a string. We can also change that index. We can change that index. If we do s.index, we can assign a new index to overwrite that old index and get first, second, and third as our new index. I saw a hand. Yes, sure. I know it's just obscuring a word here. By passing in an index. If I close this, it usually helps by index list. Okay. Let's see, still got a little bit of time here. So let's wrap up. Again, we can access that index and we can see it's been overwritten. Okay. How do we actually go select elements out of an index, or excuse me, out of a series? How do we go pick out elements? If I have this long column and I'm trying to pick specific elements, maybe with a condition, how do I actually do this? Couple ways. You'll see in pandas, there's often many ways to do the same thing. Also keep in mind, data scientists are looking up basic syntax all the time, even for things as basic as this sometimes. What is that word again? What is this? This is where large language models are really helpful. What is the syntax for so-and-so? Another way to think about LLM, that LLM conundrum I talked about before, is there's kind of 2 steps in the world. You need to know what you want to do, and then you have to do it. And the do it is where the LLM is good, but the what you want to do is the hard part. That's what you're trying to learn in this class, right? You're going to see how to do things, right? You're going to see the code in this class. But keep in mind, looking up syntax on the fly is fine as long as you know what to ask for. So how do we pick out elements from a series here? We've constructed a series. Let's say we want to pick out the first element here. we want to pick out the first element. If I want to pick out this first element, I can say, well, index into S and grab for me the value corresponding to the index A. So a single string label is going to give me back a single value. It's going to give me back a single value. How do I get multiple values out of a series? Well, instead of just passing in a single string label, I pass in a list of labels. Now, very common error here. It looks like there's double brackets, but there is an outer bracket representing the indexing that we talked about before, and there's an inner bracket representing the brackets needed to construct a list. So we're passing in a list of string labels, A and C now, to get both the 8th element and the C th element out of this series S. Again, common typo is to forget those brackets, but Python will help you. If we do this, we don't get back two values sort of written out. We get back a new series. This is just how Pandas works. If you extract more than one element from a series, you get back a new series containing those elements. If you extract just a single value, you just get that individual value. Okay, make sense? That's a series. Filtering condition. A filtering condition. So how do we extract not just with a label, we actually know what the label is, but maybe there's a condition we need. And I'd say of these three, I guess you're going to be using them all a lot, but this third one is probably the most confusing part of the syntax we're going to talk about today. So I would pay attention here. So let's say we want to extract some part of this series that satisfies a particular condition. So let's say I want to extract the first element and the last element, because notice 4 and 6 are greater than 0. So I want to extract every element from that series that's greater than 0. How do I do that? How do I do that? I can't always write out my series like this with 4 elements. There might be literally billions of elements for me to deal with. How do I deal with that? I need to provide a condition. So how do I do that? So the first thing I have to do, and I'll write this out momentarily, is I have to apply a Boolean condition, a logical operator, greater than, less than, not equal to. And this is going to create a new Boolean series that's often referred to as a Boolean mask. I'll explain why in a sec. We then apply that Boolean mask to our original series. I think it's a lot easier to see this written as code than it is written out in text. So let me show you. In the bottom left here, we are constructing a new series. We are asking the question, which elements of S are greater than 0? Notice that it's comparing the values of the series. It's not using the index here. It's using the values of the series, everything on the right. It's using those values. And we're asking the question, which of these is greater than 0? So notice we get back a new series of the same length, that's now logical, that has the same index. True, false, false, true. This is the Boolean mask. This is the Boolean mask. Why is it a Boolean mask? We can apply this Boolean mask to mask away elements of a series that don't meet the condition. So I'm now going to re-index back into my original series. This is a very, very common pattern using that Boolean mask. So I start with my original series and I index into it with this series of true and falses. If you want to write that out in English, it's saying choose the elements of S where the value is greater than 0. The value inside of S is greater than 0. Okay, so this is how we index into a series with a filtering condition. We'll be doing this a lot in Data 100. To wrap up here, a data frame, again, is essentially a collection of series that share the same index. There's the year series, there's the candidate series from that old elections data frame. We can tack on a bunch of other series and we make our original data frame. So when we say the word series in Data 100, we're typically referring to that series as a column of a data frame. The data frame is sort of the main data storing object in this class. Series are a component of that data frame. And like I said, we'll do a demo in the next lecture that covers everything we just talked about and actually doing the code live with you. So thank you all for coming today. We'll see you tomorrow and Wednesday and Thursday. Thanks again.